Hello and welcome to AVLI, AP Computer Science. My name is John Maxwell and we will be covering object-oriented programming, or at least getting a start on it today in this lesson. So before you have a class called point, and everything that class contains is in between the opening and closed braces. So the name of the class shares the same name as the file, and a class in general has two things going for it. One is the state, which is maintained in instance variables, and the other are behaviors, the way the class can act in a programming context, and those are defined within methods. But stepping back a little bit on the object-oriented approach, when we first started programming, we took a structured approach, and everything was top-down to the first line to the last line. Usually in the main method, it just ticked off one line after another and produced a result. And that was fine, and that's what we did when we first started out programming in the 40s, 50s. And along came methods, and we were able to jump out of the main method or the starting point to the software and go into a method which performed a specialized set of work. It was repeatable, we could call it multiple times, and that was a step away from the top-down approach, but it was still quite structured because it occurred mostly in one file. So fast forward to the late 60s, early 70s, we began to see a object-oriented approach. And one of the first examples was a group of computer scientists that attempted to simulate traffic in a Norwegian Ford. And so they had ship objects and dock objects and all sorts of other aspects of port operations, and they were able to put these objects together and have them interact with each other. And so the object sort of was about interaction between different objects, communication from one object to another, and that modeled a lot of the way systems work. Modern airplane has a braking system and jet system and altitude system, etc. And so different objects make up the whole. It's kind of a gestalt, out of many come one. But that was the start of object-oriented programming. And it flashed forward through the 80s and into 1995 when Java was created. It was created with objects in mind. And they're a central part of Java and many other programming languages. The creation of an object, say like a car object or such, will allow you to create child classes like sports car, SUV, mid-size sedan. All of these child classes from the original parent car class, enabled something different. But we're getting ahead of ourselves when talking about inheritance. But we do know that the base of a lot of what's going on in object-oriented programming is the class. And so it's essential to have a good understanding of it. So we talked about the state of a particular class. These are maintained in class instance variables, which are almost 100% defined as private. And that is that a point, right, has like two properties really, an x and a y. And it's hard to come up with any more for a point. Perhaps if it's a graphic, it might have a color, but we'll keep it simple. X and y, okay? And that is what constitutes a point at its elemental level. And so they're declared as private because we don't want any entity or program outside the point class to be able to make random changes without asking the class. That concept is called encapsulation, an important word. That the class handles all aspects of its own regulation and reflection. So there's a number of methods that make up the behavior of a class. A class behaves through or acts through methods, okay? And two of these are constructors. And so if I look at line 6, we can see that the constructor shares its same name as the class, which is the same name as the file. It doesn't have a return type. Notice that. There's not even a void in there, but other than that, it has a method header, very recognizable. It's obviously public, because how would you be able to create a object without it being public? Okay, and notice from another class it takes an x and a y, double x and double y, and sets the instance variables equal to those values. But because they're both called x and y, we have to differentiate for the compiler which is which. And this dot x refers to line 3, that instance variable, and this dot y refers to line 4. And so this dot x equal x sets the parameter double x and its value into this dot x, the class instance variable. Now, you'll see another example of a constructor that takes two ints, and the purpose of that is to allow the user, the end programmer, to be able to create a point in whichever way they want, with doubles or ints. Notice that it shares the same name as the class. The parameters are a and b, and so there's no confusion, no need to put this dot x equal a, because there's no confusion between which x is which. Okay, and it brings up an interesting point. When two methods share the same name, and they certainly do, lines 6 and 10 do, they're said to be overloaded if the number, order, or types of parameters are different. So again, the definition of overloaded methods are when they share the same name, they have different number, order, or type of parameter. Note, nothing in this says that they differentiate or can be overloaded by return type. All right, let's move on. Line 14 and line 17 are both examples of accessors. Hey, you want to know what my x is? Better use the accessor method. And I'll tell you, I'll have a return type of a double. So when you call getX and when you call getY, I'll give you the information contained in the private instance variables, but only through the accessor methods. All classes have accessor methods. It's just what they do. And likewise, if you want to change the x and the y, you use mutator, as in line 20 or 23, also known as modifier methods. They take in a parameter and allow the external programmer or program to change the x and y. This dot x equal x, again, differentiating the class instance variable x from the parameter x. And that's the way you change. And so let's review. We have constructors, accessors, and modifiers. 3 types of methods. And that and those define the behavior of the class. So moving down a little bit, we also have a toString method, which provides a string representation of the object. If you didn't put a toString method in, it would use the capital O object toString method, which would output the memory address. And in almost all instances, you don't really care about the memory address. You really want a string representation of the object. And in this case, it returns x plus a comma with a y. Likewise, we put on line 29 an equals method. And that takes another point other, and determines whether or not they're equal. So if x equal other dot get x and y equal other dot get y, then they're the same. The x and the y are the same. And again, you want to put an equals method in every class that you create, because without it, it will run up the inheritance tree to the capital O object, and what will be compared are memory addresses. So without an equals method, you're just comparing memory addresses if you call the dot equals method. So notice nothing in the point class has a main method, and so it can't be run on its own. A point is a service to any other program or file that needs to create a point. And it's a well encapsulated object point. It contains a way to update, a way to access, a way to represent itself through the toString, and a way to compare. So what more do you want? Well, let's see how it's used. Here we have a point tester method, and it has a main method on line 4. And in line 5, I call the constructor that takes two ints, 10 and 0. And in line 6, I call the constructor that takes two doubles, 20.2 and 10. And then in line 7, I return to creating an object with two ints. And I'm just going to comment this out for a second. That's going to come. Here we have us testing out the set y. I'm going to change the y from 0 up here to 20.2, and then I'm going to output using the getX and getY methods just to test them out and to see that they work. Then I'm going to output the P2, which is automatically calling the toString method. Again, the println and print methods of system.out will automatically look in the class to see if there's a toString method and use it to output. So you'll see that in a second. And then I'm going to compare P1 to P2 to see if they're equal. And I already know that 10 is not equal to 20.2, so I expect a false result. And that's what I get. First, I get the output of P1. Then I get the output of P2 using the toString method. And I get the answer false, because you can see from the coordinates down in the lower corner that they're not the same point. So I've tested out my point class, and it works pretty good so far, so good. I'm not really using it in a robust application, like a graphic class or anything like that. But I'm going to compare whether or not all 3 points are on the same line. Okay, collinear is what that refers to. And so in order to determine if they're all on the same point, I'm going to get their x and y coordinates. Okay, now a little bit of math here. The lines between all 3 points have to have the same slope. So P1 and P2, the line connecting those points has a slope. The line connecting P1 and P3 has a slope. That should be the same slope. P2 and P3 should be the same slope. The slope should be all the same. But you could also say that the y of one point should be located on the line of the other 2 points. Okay, so let's go with that. First, we calculate out the slope of P1, P2, the line connecting P1, P2, and we output it. And then we find the y-intercept of that line, okay? And, we output it. And then we ask if the slope times x3 plus the y-intercept is equal to y3. They should be if they're all on the same line. And so let me just test that by uncommenting out this is online method. Okay, scrolling up, we see the slope, 0.98. Guess so. The y-intercept, negative 9.8. Very interesting. Okay. False, they're not on the same line. So y3 is not found on that line, not equaling the y-intercept of that line. And the rest is what we've covered. So this has been based on 2010 FRQ, and I'm going to jump over here and show you. Okay, here it is. There you had to create your own AP line, okay, and they gave you complete instructions on how to do that. You got credit for having a constructor, okay. It also had a get slope method, and it had an is online, okay, and that's where some of that formula came from. Okay, so you can take a look. The 2010 AP CSA free response question number 2 is online. Hopefully this has given you some good sense of object-oriented programming. It starts with the creation of a class that has instance variables and methods of the type constructor, accessor, modifier, and from there it can go almost anywhere, and the sky is going to be the limit for our semester here. Thank you for watching. This has been AP Computer Science A with the Arupe Virtual Learning Institute. Thank you.